Okay, now let's discuss concept of electromotive force. For a steady current, a conductor must be a part of a path that forms a closed loop or complete circuit. Uh, if we establish an electric field inside an isolated conductor with resistivity rho that is not part of a complete circuit, a current begins to flow with current density J is equal to E1 over rho. Let's suppose I have a closed circuit and it cut as some part of the conductor, and now it is in an isolated form. If an electric field is produced inside a conductor, that is not a part of a complete circuit. Current flows for only a very short time. So as a result, a net positive charge accumulates at one end of the conductor and a negative charge accumulates at the other end of the conductor. Okay, these charges themselves produce an electric field E2 from here, from this towards this direction, positive towards negative, and this is opposite to the E1, and it of course the total electric field and the current decreases. So within a very small time, enough charge builds up on the conductor ends, and that the total electric field becomes zero inside the conductor. Then J becomes zero and the current stops altogether. So there is no steady motion of charges in an incomplete circuit. So how to maintain a steady current in a complete circuit? Let's recall a basic concept of electric potential energy, in which if a charge Q goes around a complete circuit and return to its starting point, then the potential energy must be same at the end of the round trip as at the beginning. But there is always a decrease in potential energy when charges move through through any conducting material with some resistance. It means that there is something in the circuit which increases the potential energy. So we can resemble it with the water fountain that recycle its water. When the water pours out of the openings at the top, it cascades down over the terraces and spouts, and then collects in a basin in the bottom. Then there is a pump that lifts it back to the top of the top for another trip. So without the pump, the water would just fall to the bottom and stay there. So it's the same here in a circuit. There must be some pump, there must be something which increase the potential energy again. So in this device which uses a pump, there is a charge that travels uphill from lower to higher potential energy, even though the electrostatic force is trying to push it from higher to lower potential energy. So the direction of current is in such device is from lower to higher potential, just opposite of what happens in ordinary conductor. So this influence that makes current flow from lower to a higher potential is called electromotive force, and we abbreviated it as EMF. And this is not a force, actually it's an energy per unit charge, like a potential, and its unit is volt, and 1 volt is equal to 1 joule per coulomb. This typical flashlight battery has an EMF of 1.5 volts, which means that the battery does 1.5 joule of work on every coulomb of charge that passes through it. So in every circuit, which in a complete circuit with a steady current, it must include some device that provides EMF. So this such type of device is called a source of EMF. And batteries, electrical generators, solar cell, thermocouple, fuel cells are some examples of sources of EMF. All these devices convert energy of some form into electrical potential energy and then transfer it to the circuit to which the device is connected. And so an ideal source of EMF contains a constant potential between its terminal and independent of the current through it. So this is a schematic diagram of an ideal source of EMF that maintains a potential difference between conductors A and B, called the terminal of the device. And this is the source of EMF. So the terminal A is marked positive because it is at higher potential. This is terminal B is marked negative, it is at lower potential. So because of this potential difference, there is some electric field in the region around the terminals, both inside and outside the source. So the electric field inside the device is directed from A to B as shown. A charge Q within the source experiences an electric force Fe, which is equal to QE. But the source also provides an additional influence, which is non-electrostatic force, Fn. This force is operating inside the device and pushes charge from B to A in an uphill direction against the electric force Fe.